Hello, everyone. Welcome to the video abstract of our publication on Journal of Navigation. My name is Yunxiang Liu, and usually I go by Leo. Before I start the presentation, I would like to acknowledge and thank Dr. Yang, Dr. Li, and in particular my advisor, Professor Jen Morton. Their help went a long way towards developing the methods I will be sharing with you here. This work is from the Satellite Navigation and Sensing Lab, known as SENS Lab, in University of Colorado Boulder. The title of this work is Spatiotemporal Deep Learning Network for High-Latitude Ionospheric Phase Scintillation Forecasting. Here is the motivation and objective. Ionospheric phase scintillation refers to rapid phase fluctuation of GNSS signals propagating through ionospheric irregularities. The reason we care about scintillation is that its occurrence may lead to degradation of precision, service discontinuity, or even outage. So the objective here is to forecast the occurrence of scintillation by using machine learning. This slide shows the machine learning-based forecast framework. Given the historical measurements as input, the feature engineering first groups measurements, which we call features in machine learning, based on their time steps. Here, feature engineering is the process of using domain knowledge to extract features from raw data. Suppose Tn is the current time, and Tn minus k is the time that is k steps to the past. Historical measurements from Tn minus k to Tn are used as features and input to the machine learning algorithm. The objective is to forecast whether scintillation will happen at Tn plus m in the future, which is a binary forecast problem. In this study, we set the lead time to 1 hour. And by setting up the features like this, we can preserve the temporal information that can be utilized by machine learning algorithms we proposed. So let's talk about what historical measurements we can use. The icons shown in the left plot are locations of GNSS stations. The blue icon at Poker Flat is the target station, so the objective is to forecast the scintillation for this particular station. Of course, historical measurements from this station are very important information. Since the high-rate data is available, we use the historical measurements of S4 and sigma phi as features. Here, S4 is the amplitude scintillation indicator, while sigma phi is the phase scintillation indicator. The yellow icons on this plot show surrounding GNSS stations from public GNSS network. And these stations roughly sense nearby ionosphere, which provides special information for the forecasting task. As only low-rate data is available, we use another disturbance indicator, rate of TEC index, ρT. The historical measurements of ρT are used as features. In short, we use historical measurements from target and surrounding GNSS stations as features. And what else can we use? The plot on the left shows from Earth to Sun at the Lagrange L1 point in between. We have used the GNSS measurements collected from Earth's surface. We can also use space-based observations like solar wind parameters, and ground-based observations like polar and auroral indices, storm indices, etc. as features. And these observations related to the drivers of scintillation occurrence, which can provide useful ahead-of-time information. And eventually, all of these features are input to the machine learning-based forecast model to forecast the scintillation. Here is the implemented machine learning algorithm. Given the features from target and surrounding GNSS stations and space-based and ground-based observations, we apply this spatiotemporal deep learning network architecture to adaptively incorporate the information. The inputs are measurements from target and the surrounding GNSS stations for each time step. They are first passed to a spatial fusion module to adaptively construct the most informative feature vector for each time step. Then the fused features from all time steps are passed to a temporal fusion module to adaptively incorporate the temporal information. In the meantime, external features like space-based and ground-based observations are also input to the forecast model. And eventually, this model forecasts the probability of scintillation occurrence and time Tn plus m. And this slide shows the performance evaluation. Two extreme examples are shown as threshold equals to 1 and threshold equals to 0. And by varying the threshold from 0 to 1, we can obtain a receiver operating characteristic curve, also known as ROC curve. It should be noted that in order to have a systematic performance evaluation, we evaluate the performance on this curve instead of a single threshold. And for the ROC curve, the higher the curve is, the better the performance is. We compare the spatiotemporal network in red with 5 other methods, the naive method, and 4 machine learning algorithms, logistic regression, neural network, LSTM, and the GBDT. And here I want to emphasize again that these 4 machine learning algorithms use the same features as spatiotemporal network. The only difference is how each algorithm handles the feature. It is clear that spatiotemporal deep learning network is the best across all thresholds. And the commonly used metric to evaluate this curve is to compute the area under the curve, shown in the table. Again, ST is the best. The best performance of spatiotemporal deep learning network shows that the network can adaptively utilize the spatiotemporal information, where other methods fail to do that. Recall that in addition to the GNSS measurements, we have also used external features like solar wind parameters. Both are employed as input to the spatiotemporal deep learning network to forecast the scintillation. Here we investigate the importance of these external features. And by excluding the external features, we could forecast the scintillation by only inputting GNSS measurements to the model. Then 2 setups are compared against each other. ST in purple represents the best performed spatiotemporal network we have discussed in previous slides. ST no ext denotes the spatiotemporal model excluding the external features, and only GNSS measurements are input. Here are the performance comparison between these 2 setups. ST in purple and ST no ext in red. Clearly, we can tell from this plot that spatiotemporal model excluding external features demonstrates a dramatically performance degradation. And this investigation demonstrates that external features are very important, which provide critical ahead of time information for the forecasting task. And more details of this work can be found in this journal listed here. And if you have any questions, feel free to reach out to me via this email address. In addition, welcome to explore more research work from our lab led by Professor Jen Morton via this lab website. And finally, thank you so much for your interest in our work.